All right, so today is going to be a bit unusual, so hopefully you watch the video. Today we're going to learn about RedBlack trees, which are from all the way in Chapter 9. But I figured since we have time, because we're doing good time in this class, we might as well slow down and take something from Chapter 9, which I normally don't do, and we're going to do it as a class exercise, because RedBlack trees are a pain in the butt. They are a real challenge to code. I think like the most line efficient one that somebody came up with was like the add method taking 41 lines of code compared to the one I had. So it's just because they have a lot of exceptions to them. So first thing you want to do is maybe, so actually, let's go ahead and just ask, like, so a RedBlack tree, right? That's, yeah, so there's my mug, okay. So there's a there's this thing called a RedBlack tree. It's a, let me tell you now, it's a binary search tree. It's a special type of binary search tree. Why would we bother putting it in its own, as a section in a chapter somewhere in this book? We're learning about binary search trees, so what would make this binary search, this RedBlack tree, something worthwhile to learn about? What possible feature might it have that we might really like? Just as a review of the features of trees. So what's the worst case scenario of what can happen with the tree? Do you remember that? And so let's go and look at the slides. Oh, no, wrong slides. Kaufman. Okay. And by the way, your book has the code for a binary tree. So let's look at the title for this chapter. Self-balancing search trees. So a binary search. So this tree might be. So RedBlack tree is a self-balancing binary search tree, which is what makes it special, right? Right, the performance of binary search trees, if you remember, the amount, we haven't gone over the big O times for add or remove yet, but we've mentioned them previously. We haven't, like, analyzed the add and remove method, which we should, which we're probably going to do later tonight. But if you go to, right, if you've got n items in the tree and the tree is balanced, meaning that basically everything's at the same maximum height, right, then each choice you make, right, that would ideally throw away half of your search space, right? That would toss half of your search space out. So you go left, you throw out all the stuff greater than the item you're searching for. You go right, you throw out all the remaining stuff that's less than. You've only got a quarter of the amount of items left to search, right? But this only works if it's balanced, right? These are two examples of unbalanced trees where you have a log n, where the lookup time isn't log n, but it's O of n. Right here, if I want to find things, I have to basically, this is a glorified linked list, right? It's just a linked list on an angle, okay? More realistic but unbalanced tree is something like this, where you have the occasional branch jutting off to the side, but notice it doesn't actually do anything for you, right? The quick round up, you know, these things that are jutting off to the side, they don't actually help sort the tree at all, right? They're dead ends. They don't help branch the tree. They don't reduce the search space if I take a branch. In fact, they're just, I found that thing that I was looking for. So those, so that's kind of why, so obviously balance is an important thing to have. So there's, I'll get into this in a bit, but the focus of today is learning this operation, which is called rotation, which I'll get to it. But most of the time we fix the binary tree by doing something called rotation. I'll come back to that in a bit. But let's learn about the RedBlack tree. So I'm going to go with like why we care about rotations, because they're used in self-balancing binary search trees. But I'm going to talk about them. So so in classes you'll typically learn about two types of trees, like a self-balancing. If you're taught a self-balancing binary search tree, you're going to be taught one of two: AVL trees, which are named after Adelson, Velsky, and Landis. Who, this guy probably butchered his name because he's got a lot of it. Diuretic marks. And that's a self-balancing tree that just basically, again, it just detects whether they're unbalanced and then they'll rebalance it using this rotation exercise. So and if you're interested, look it up on your book or look it on Wikipedia. In fact, that's what we're going to do right now. I'm going to go over it in Wikipedia once, and then I'll go over it in the slides, what RedBlack tree looks like. And then we're going to work on programming the rotation methods. Okay? So, let's go ahead and look up RedBlack tree. So RedBlack trees, the reason we like that, they're nice, is because they're relatively easy to understand the concept. want to build one on your own, you're more than welcome to do that. I might let that be an alternative to the assignment I'm going to give out this weekend. Sorry, this week. So it's not going to be perfectly balanced, as balance will be defined, but it's balanced enough that basically that it's going to make sure that everything happens in O of n time. But basically, it means that we just add one bit of data, like literally one bit of data to the node, if we were going to be super optimal about it. Typically, in Java, what we're going to add is a Boolean, and that's something to represent the color of the tree, whether it's red or black. That's all that. So that's all that gets added to a RedBlack Trees nodes, whether it's red or black. So it's pretty much no extra space for these. Okay, and then we have rules. So here's a RedBlack tree, an example RedBlack tree. Okay, notice that basically it's a binary search tree. The two main differences are that the nodes are colored, they're either red or black, okay, and that the leaves of the tree are, the nils rather, the null points of the tree, they're actually drawn on the tree. Sometimes you don't have to draw them, but that's just simply that. So these trees typically have 5 rules, sometimes they're 4. The first rule is that each node is either red or black, which we already knew, right? So, okay, that wasn't too hard. Okay, so nodes can be either red or black. Rule number 2, the root is always black. Okay? No matter what we do to this tree, the root is always going to be black. Rule number 3, the leaves, or rather specifically not leaves, but the nulls. Okay? It considers some interpretations, they consider these leaves, the trees, the nulls. I don't, but basically the nulls, anything that gets pointed to that's null is black, right? So your root is black, the nulls are black. Okay? Rule 4, if you're red, then both of your children are black. Okay? And then the last thing is the supportive rule that we build up to this. Every path from the root to any of its descendants should contain the same number of black nodes. So notice that basically 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Basically, including the null point, it takes, if we take any path, it's going to have 3 black nodes in it. Okay? Right? 1, 2, 3. If we count the nulls as black, otherwise you're going to have 2. Okay? If you don't count those. So that's pretty cool. And what this means is that as a result, because of the way this is built, you're never going to have more than twice the number of black nodes, twice the, essentially this means that the path from the root to the farthest leaf is never going to be longer than the longest path. It assures that basically the shortest path and the longest path are never going to be twice each other, more than twice each other, as a result, because of this rule. Because if it weren't, we'd have more black nodes than the other one. Yes?
Is it like alternating?
It sometimes does. It really depends on how we add it. Typically when we add a tree, which is add a node, we add a red node. And then we figure out, okay, well, if it's like, say we're adding 28 here, right? Well, over here, if I'm adding a red node over here, then we start after thinking about what rules we need to change. If I add a new red node over here, because remember, 27, it's supposed to be, the 27, it's supposed to, since it's a red node, its children have to be black, but I'm added a red node. So it says, okay, maybe one of the changes you might do is say, okay, I'm going to change 27 and 22 to black, and I'll change 25 to red, only that won't work. Right? There's kind of this algorithm that basically recolors the tree, and by recoloring and doing some rotations, it's able to figure out. Basically, what you add, just like, what makes this a useful teaching tool is that you add, just like you would a node, you add just like you would any other tree. You add and you delete as normal, okay? Just like a binary search tree, okay? Those don't change. What happens is afterwards, after you successfully add or remove, you say, okay, now let me rebalance the tree. So you assume the tree is already balanced, and then you say, okay, by adding this node, have I unbalanced the tree? And there's all these scenarios. There's like literally 5 cases when you add a tree that say, oh, we need to check basically, did we add a root node? Is my parent black? Is the parent red? And my uncle red? Right, so my parent's sibling, is it red? Right? am I red and my uncle is black, right? That is something weird going on there. So basically it's got all these cases that say we need to change the colors of stuff, or maybe we need to rotate things around in the tree. But by basically checking these things out, checking to make sure it's just a bunch of if statements essentially that basically say if this case, then if this case do this, then if this case do this, they all just follow each other. And so it takes 4 cases for adding and 5 cases for remove. So it ends up being at least a lot of discrete things. I used to give this an assignment at another school, but they didn't learn hash tables, which we want to learn, and they didn't go over the sorting algorithms in as much detail as we do. In other words, I like to hit a lot. I've learned that basically I like to go for quantity in this one, while basically giving as much of a deep dive so we can get as much quality as possible. So I just wanted to say that these things exist. So here's another way that the slides talk about them. Right, so they're in the slides. In fact, your code for these things is in the book. So again, here's the rules, except they have 4 rules here. The node is either red or black. The root is always black. A red node always has black children. Nulls are black, right? So they took out the rule about the leaves being black, right? That it says that the nulls are black, and they just simply combined it into here. And you always have the same number of black nodes from any path from a root to a leaf. Yes. Sorry, I thought that was a question. Yeah, counting. Yes. So height. So essentially you determine height only by counting the black nodes, and it's always balanced because the nodes right and left subtrees have to be the same height, right? The left and right subtrees over here, they have the same quote unquote height, even though they're black nodes. And basically we know that the maximum length here is 2. This path is 2. This is 4, but we know that's never going to be more than twice what the shortest path is. So it's never going to be worse. And then there's all these cases which they go over to, and they basically say, okay, we violated these invariants that we set up, so now we have to fix that case. And then we fix it by rotating a lot of the time. So what the heck is this rotation operation? It's actually it's one that I find that's very good at getting your mental muscles flowing, which is exactly what you need when you come back from a nice break. So here's what we're going to look at, the algorithm for rotation. What a rotation does is that it fixes a tree. It turns a tree on the head. A rotation is an operation that changes the relative heights of the tree, but it preserves the binary search tree property. Now there's 2 rotation functions, but once you figure out one, it's easy to figure out the other, just like when, like if you're adding to the left side of the tree, you figure out how to add to the right side of the tree as well. There's a left rotation and a right rotation, and this one's a right rotation, I believe. So this is the operation that happens, right? So this is what we call a rotation operation. So notice how this tree is kind of unbalanced, right? This is the before, and this is the after over here. Notice the after, where basically the heights, now it's a much more balanced tree. Everything's at height 3. Here, we're at height 4. So what a rotation operation does is that it fixes the tree. It says that basically, okay, I'm going to move 20 down and move 10 up to be the new root, because moving 10 up will make the tree much more balanced. Okay. So what happens here? Well, here's what happens. Well, basically 10 throws his right child away, right? Throws 15 away, and 20 catches it. Okay. And then 10 replaces 15. Sorry, 20 replaces 15 as 10's right child. So basically, his right child becomes the root's left child, okay? And then then the root's left child actually kind of becomes his parent. So it makes it so by doing these operations, and it takes about 4 lines of code for just to flip the pointers around, it doesn't take much effort at all to rotate the tree to do this. There are a couple considerations to make, like this operation can be performed on because remember, every node is a tree, right? Every node is the root of their own tree, right? So there's one consideration that you should keep in mind that really doesn't get elucidated a lot, which is how does a parent know that the stuff beneath him rotated, right? So that's a challenge. What I just suggest doing for the purposes of this exercise is for the rotate operation to return the new root of the subtree so that their parent knows about it. Yes?
How do you decide which node to
It's always if you're doing a right rotation, it's always this way. So let me go ahead. It's always the same. Yes. So if I'm going to the right, it's always going to be my left child that's going to be the new root because I'm moving to the right. Okay. In fact, so let's go ahead and look at this algorithm. So here's the same. This is the same tree, by the way. Just it's a bit uglier because we're pointing out the actual pointers and stuff, right? Here's the root. Here's his left. Here's his right. The right child doesn't have any children, but his data is 40. Right? Here's 20, 10, 15, 5, 7. Everybody's still there, right? So first thing we need to do is, because we're going to be swapping pointers, we definitely want to store my left child in temp, because otherwise, if you remember for the linked list, right, what could happen if I forget to point to somebody, right? I'm going to lose that entire subtree if I don't set him up as a temporary pointer. Okay, so temp is equal to root.left. Then set root.left. So set root.left to temps.right. So I grab my left child's right child, okay, and make him mine. I set root.temp. So I set temp.right to root. So now I point over here and make temp the root. So now they're just kind of dangling like that. So notice that this guy's now the root. Now what's very interesting is that the entire from this operation is that the binary search tree state of this, it didn't change. We don't have to reorder anything else. Everything is still in the binary search tree order, right? Let's look over here. After doing this, all the stuff that's less than 10 is to the left of 10. All the stuff greater is to the right. Yes?
Is there any benefit to the RedBlack trees?
It ensures that basically we don't. So the benefit is that we ensure tree, right? It will rearrange the nodes so that it becomes a balanced tree. And it will do that by changing their colors and then rotating them as needed. So that's the point of rotations and for RedBlack trees, is that they ensure that we never have an O of n time to do this. It's always going to be log n time for every single operation, right? Because worst case scenario for a balance for a binary search tree, it's O of n time to do everything. And here we're ensuring that everything is log of n by ensuring that also the rotation operations, so that takes a constant number of operations, by ensuring that basically rebalancing the tree takes a constant number of time, no more than log n time, then basically it's log n to add, log n to rebalance, so it's still log n time. So, all right. So, and I find actually the best resource for you got. So, what I'm going to find. So again, Wikipedia is actually a great resource for data structures. Like your history of paper teacher may say it's a terrible source for but mind you, you shouldn't cite Wikipedia in like a research paper or anything like that anyway, because Wikipedia, being an encyclopedia, is not a primary source or a secondary source to cite. It's actually like a tertiary source. You don't cite those kind of sources in research. They're there for reference. But anyway, I find it a great reference. So tree rotation, which brings up probably this, Wikipedia article, which has, of course, makes it look scary because it has Greek, right? That's something you'd find on a textbook diagram. So instead, have a GIF, right? So that's basically the way these things work, okay? And they go in, so you can look up this page as a nice reference, right? That's a nice GIF. It has, this is how you do a right rotation. This is how you do a left rotation, right? So if you do a right rotation followed by a left rotation, you end up with the same thing. There's a detailed thing over here, so it defines it as the root and the pivot. But you can follow these. So what I'd like to do for our in-class exercise today, and I'd probably just like to spend no longer than a half an hour to 45 minutes on it, is going over, is basically I want you to pair up and code these operations. Well, okay, how do I know if it works? Well, fortunately to you, I thought of that. So let's go to my GitHub page. the easiest way for you to find this stuff rather than me posting it. GitHub.abrosen/classroom. Okay. If you go into data structures and code, and if you go to trees, you go to my binary tree. Well, add yourself. Well, all you have to do is add for yourself. You know, grab my code or whatever. If you wrote the code as well, if you were following along, you can do that. You can grab this, but grab my code, right, which has the add method and the remove method, right? And I've added a toString method that I did previous semesters, which does a pre-order traversal of the tree. And what it does is that I'll show you actually on here. What it does is that it does a nice indented printout of the tree. What it does over here, under, let's see, so, oh, this is the teaching folder, not the, so, open. Yeah, the only thing I don't like about this is that I can't have, like, multiple projects. So, new window. So, yeah, so binary tree. So if I go into binary tree, right, and now if I print out my stuff, it's going to print out. It prints out my trees now. If you use my code from GitHub, the tree now prints out like this, where the root is on the first indent, his children are on the second indent, and their children are on the third indent, right? So 5's children are 12 and 0. 0's children are 2 and null. 2's children are 4 and 3. 4's children are 3 and null, and 3's children are null, right? So basically, it doesn't do left and right because, of course, it's just simply because that's a bit hard to do. Rendering binary search trees in text is really hard, but this allows you to look at a node and see who are my children, who are the children. So if you rotate, and the nodes are in a different order, but they're still in a binary search tree order, and all the nodes are still there, then congratulations, you successfully rotated the tree. So pair up. So pair up. So find somebody to pair up. This is a pair programming exercise. On Canvas, when you're done, you'll want to submit. So canvas.edu, go to here, click the link. And then there's under the quiz grades, there is under assignments, there will be a RedBlack Dropbox, okay, for you to jump on, okay? Yes?
This is 1 point.
Sorry, yeah, it says this is worth 100 points. That's wrong. I gotta edit that. That's worth 10 points. This is worth as much as any other quiz grade, right? Again, I like, my quizzes are not really quizzes. They're participation kind of things, but, so really what I want you to do is to put in the, again, I want you to implement the left rotate function and the right rotate function. And remember, you'll want them to return sorry, you have okay. You want to implement a right rotate function and a left rotate function. They're about 4 to 5 lines long, 5 if you include the return statement that you need to include, which is that you should return the new root. Right, and so I'm simply going to close the recording, and then I will walk around it and pretend to help, I guess.